All right, so I think we can start the recording. So today we are going to prove the Morse or sketch the proof of the Morse Smale Witten chain complex, uh, which is like the tells you how that Morse functions can see and can detect homology of manifolds. Right, so let me recall it. Suppose we have a function f from M to R. So M is a closed manifold. And let crit K denote the set of all critical points of index K. So F is a Morse function and we have psi a gradient vector field. Define CK to be the free abelian group of rank crit K, or a space generated space, a vector space spanned over the set of critical points. The elements of CK, or maybe X is a better letter. So sum of AI classes of PI, where PI is a pair PI epsilon I, actually. So PI is a shorthand for PI-EI. PI is a critical point of index K, and EI is the choice of orientation on T PI of the unstable manifold. And then with this choice of orientation, we have CK. We have the map CK going from CK to CK minus 1, where given by the class of PI is mapped to the sum of NP IQJ, QJ, where NPIQJ is a signed count of trajectories. All right, and the theorem is that, let me just write it over here, because that dk minus 1 composed with dk is 0, and kernel of dk divided by the image of dk minus 1 is isomorphic to h k of mz, where hk of z is the singular homology of the manifold M. The proof, okay, this condition is known as a condition of a chain complex. So there is an object in mathematics. For those of you that do not know, there is, but probably most of you know, that there are objects in mathematics that are chain complexes. So these are sequences, finite or infinite sequences of objects. Finite or infinite sequences of objects with maps between the two consecutive ones, such that the composite is 0. Like one of the most prominent case is if you have the d square of the of a differential form, then this is zero. Okay, and like most of calculus 2 that you have been taught is consists of checking for or looking for differential forms that are in the kernel of the map D, so the kernel of the derivative, but are not in the image. So the forms that are exact but not that are close but not exact. So these are measured by a topological object, like in here. And so there is a stage in the education process of a mathematician that where you just love homologies, but then you see that chain complexes are much better than homologies. You will see that in the future. You will see that in future. Okay, so this is a chain complex, which is called the Morse Smale Witten or Morse Witten or Morse chain complex that computes homology. So this is the theorem.
I'd like to ask about the definition. What do we mean this by the sign count of trajectories and
Okay, so we have a Morse Smale um, uh, uh, Morse Smale Morse Smale vector field. Okay, so this is from last lecture. We have two critical points whose indices are differ by one. Okay, so we look at the intersection. Is it here? Yes. Let's see here. We have a stable manifold. Sorry, unstable manifold of the lower critical point. It's intersected with the level set. It's F inverse of C. And then there is the stable manifold of the other critical point. That is that intersects with the level set in between, which is denoted by B. So we have A being this and B being that. And we say, okay, we have orientation in here. We have an orientation over here. So we can define the intersection index of A and B because they have complementary dimensions. So
Okay.
this is like, or you put, but the way, that's the formal definition. The way we think and why it's called the sign count is that each point of intersection carries a sign. And this sign is defined as the, uh, mm, uh, like, whether the corresponding orientation is plus or minus one. And if you say signed count, it means you count points with signs. So some points contribute plus one, some points contribute minus one. Okay? That's the, or so let me come back to the present lecture and let me start proving it. In the proof I follow, well, this is not a proof. This what I give is the idea of the proof that is contained in section 2.5 of Nicolaescu's book. So invitation to Morse theory. And I chose this because it's the conceptually the best. It tells you what is going on. And like Baniaga Hurtubis gives give many more details, but not all the details, but they give enough details so that you have real troubles understanding it. And there is the Salamon's paper, which is very, very, very nice to read. It's a survey with an enormous amount of citations. So it's the paper from like 90, I think it's 1990. So it's Morse theory, Conley index, and Floer homology. And this gives a proof that is conceptually the same as in Baniaga-Hurtubis, but Baniaga-Hurtubis give much more detail. And there is also a proof of that fact in Kronheimer Kronheimer, Mrówka in the book, but they give proof by proving a more general statement in Floer homology like this infinite dimensional spaces, and this proof is and then they specialize to Morse theory, but the statement is there. And there is one of my favorite proofs in Blaine Lawson 2000, around 2000, in the Annals paper. And if you love geometric measure theory like currents and Pfefferman theorem and so on, then I advise you to read this book, this paper. It's very hard to read because of many details put under, well, many things that are not written. It's not very well written, but the ideas in that paper are excellent, and there is a plenitude of things that you can prove if you read this paper, new things that you can prove if you read this paper and understand it. So, and maybe we can come back to it during classes, but I think it's more like voting. So if some, like 1 or 2 people read this paper or this one and want to have it discussed during classes, then we will discuss it during classes. That's what I call by democracy. Okay, so let me pass to the proof of the facts. So first of all, we can assume that maybe I will copy this picture for the next page. Oh, next page is also taken. Okay, let me stay in here. So I should be able to add a page between, but add a page before. Okay, current template. Oh, that's fantastic. And I'm here and I'm here. Okay, so proof. 1. Assume that f is ordered by, or it's I will call it. So let me just say one more word about it. So we have critical points of f. We look at critical points, and then these critical points, well, they can have different values. So rearrange the critical points in such a way that if P is a critical point of index K, then f of P is equal to K. Sorry, not Fk of P, but f of P. So what can we do? We have a gradient-like vector field xi, which is Morse Smale. So d xi f is greater than 0. And then we can rearrange. So we just start rearrangement. And we can always rearrange in such a way that the critical points of higher index have higher critical value than the critical points of lower index. Okay, that's what we can do. And what we can do with critical points with the same index, well, we can shuffle them as we please within the limits provided by the critical points of different indices. Okay, so you can, if you have 2 critical points of index 3, you can make them either one critical point is above the other or the opposite, but your limit is that you can't put the critical point of index 3 below the critical point of index 2. Okay, so you can shuffle. And you can, with this freedom that was given to us with during the proof of rearrangement theorem, we can use this freedom or abuse this freedom to put all the critical points of index K at the same level. Why am I saying abuse? Because like from the perspective of self theory, which we will discuss later on, there is no critical points. Having 2 critical points of index is something that is not desired. But in this case, we put all critical points of index of index k at the same level set, and then next critical points of index k plus 1, and then we just rescale the function in such by post-composing it with some like lambda, where lambda goes from r to r is an increasing function in such a way that that the critical values of critical points of index k are equal to k. So this is like a simplifying notation. What happens with index k is the critical point of index k. And note that this rearrangement doesn't change the chain complex. That's a fantastic thing, because the chain complex that you start with is not built with function f. It's built with stable and unstable manifold psi. Okay, so it counts trajectories of psi. And the rearrangement theorem, as you might remember, doesn't change the vector field psi. It changes the function only. Okay, psi, if you rearrange critical points using the rearrangement theorem that I gave you, if psi was a gradient-like vector field for the function at the beginning, it is a gradient-like vector field for the function at the end. This is a fantastic property, and it means that the space and the signed count doesn't change. Okay, so we can assume that it is rearranged. And then we introduce some notation. So maybe I can also do this. And just count this part, and because I'm introducing some notation. Cut. Paste. Okay. So this is a bit awkward, but it's more convenient. So let me introduce some notation. So the dimension of m is equal m, and I have level set. I have drawn it before, so I have level set of the function, which are k plus half and k minus half. Okay, so all the critical points of index k sit in this step. So mk k plus 1/2, and yk is f inverse of k minus half, k plus half. And then also I can choose, I can define that d minus of yk is the lower boundary, so it's f inverse of k minus half, and d plus of yk is f inverse of k plus half. Okay, so this is d plus of yk, and this is d minus of yk. All right, so let me just now what do we do? We know that here we have critical point of index k. So let me just say mk plus 1 arises from mk by adding some number of k handles. What is a k handle? A k handle is dm dk cross dm minus k attached to, this is d minus of k along s k minus 1 cross d m minus k. Okay, that was the statement from the rearrangement theorem. So what does this tell us on the level of homology? So now there is the key observation. What happens with homology? Hj of yk d minus of yk. So what is this? Well, we know that yk, or so let me just add it like this. So mk plus 1 is equal to union of mk union some disconnected sum of sk minus 1 cross dm minus k. And let me keep track of one thing. We keep track of this sk minus 1 times d minus k as each critical point of index k corresponds to precisely one copy of that object. Okay, because that's what happens. We have different handles that are attached. And why is it? Is it clear that it's the disjoint sum and not that they don't intersect?
Oh, that's intuitive, but I'm not sure if why it is so formally regressive.
Okay, so these are like stable sk minus 1 is a stable manifold to the critical point, and stable manifolds of two different critical points are disjoint.
Right.
Okay, yeah. And this is like if you cross it, means that you thicken this stable manifold. So you can thicken, if you have two closed manifolds, you can thicken them in such a way that they are disjoint. So these guys are pairwise disjoint because they correspond to stable manifolds of different critical points.
Mm-hmm.
Okay.
Yeah.
So this is disjoint. So now let me just write some. What is Hj? What is the relative homology group of MKZ? All right, so this now, and of course here we use the fact that it is homotopy equivalent. So, any ideas? All right, so let me just write it in this way. This is I think the most important step. It's the easiest step in the proof, but it's the most important because it tells you what is going on. So we have this. And now there is an axiom of homology, which is called excision. So when I was young, I didn't like excision. I loved Mayer-Vietoris sequence. We will come back to Mayer-Vietoris sequence in a few minutes. But excision, and then I learned from old mathematicians that they use excision all the time. So excision tells you that if you have H star of AB and C is a subset of B, then basically H star of A minus C, B minus C, this is the same. That's essentially what excision means.
So we could cut off MK so that we get a disjoint sum.
Well, almost.
Oh.
We can't cut off all the MK. We can cut off everything that is below. That is, we would like to cut off MK, but it's not exactly what we do. So we have excision. Hj of sorry. This is wrong. I'm saying crap here. This is of course dk, and the sum is along sk minus times dm minus k. Sorry about that. So I wanted to be too fast. dk cross tm minus k, but now the relative part, it's not empty because otherwise it wouldn't change topology, okay? The relative homology group would be the same. So look at this picture. You have the disk. Here is dk. So when you cut off everything in here, what remains, what you can't cut off is this part. Because you can cut off only open subsets. So you can't cut off. So what remains after you cut off everything is the disjoint sum of sk minus 1 dm minus k. So this is, well, now you have spaces that are multiplied by the thickening, but this thickening doesn't tell you any, is just doesn't change homotopy type. You can just forget about this thickening, or if you prefer, you can use Thom isomorphism or QNet formula for multiplying with an object that has homotopy type of a point, but it's just thickening. Hj of the disjoint sum of dk modulo disjoint sum of sk minus 1 with z. All right, so far so good. This is the most important part, that this homology is the same as the homology of that guy. And if you look at clearly at the examples where you have homology, relative homology groups, then this is what is a relative homology group? Relative homology group is something that is generated by cycles whose boundary is cycles in here whose boundary sits in here. But these are the generators. So the key point is that the construction of MK is that the generators are precisely these guys. So this is equal to the, well, now you can, for example, collapse these guys to a point. To get reduced homology of the wedge of spheres, k-dimensional spheres. Okay, so there is this crit k if j is equal to k and 0 otherwise, with the some care that should be done if k is equal 0, but that's left as an exercise. The formula is the same. So what is going on here? Here I have relative homology group, and the relative homology group can be passed to the reduced homology group of the quotient. So when you collapse this to the base point, so when I collapse, I get the wedge of, so that I have a wedge of spheres k-dimensional. So that's the picture is that you have a disk, you collapse it, you collapse the boundary, you get a sphere. So that's the sphere, okay? And then here is the isomorphism, the homology of the sphere. You remember the homology of the sphere, okay? The homology of the sphere is 0 in dimension, is z in the top dimension, z in the 0 dimension, but you use reduced homology, so you forget about 0 dimension, and 0 otherwise. Okay, so here is one subtlety in this isomorphism. You know, or maybe I should add here. we know that H J of Sk Z is Z if J is, or reduced if J is K, 0 otherwise. Okay, but we have two isomorphism of, we have an automorphism of Z. Okay, we can choose, we can map the generator of this to +1 or -1. What is the choice of generator? What is the choice? What gives us a choice of an isomorphism of the top homology group of the sphere with Z? Any ideas? Just think about it.
Orientation, I think.
Orientation, that's a perfect answer. The orientation. So what is the orientation? This is this is precisely the orientation of this space, which comes back to the orientation of this space, which essentially is the orientation of the stable manifold to the critical point. Okay, so that's why. So we have an isomorphism, but the isomorphism of this space to that space maps, assigns to each critical point of index K plus the orientation an element in this group. So we have an isomorphism Z critical K with HK of MK minus 1Z. And let us record for Z is equal to 0 for J not equal to K. Unfortunately, we will have to use this fact as well at some moment, okay? Unfortunately, because this will be the most painful step. But this is like a natural, well, maybe not natural in the sense of algebraic topology, but it's like a natural from the common sense terminology. Like we have a homomorphism, an isomorphism between this space and that space, and we know that this homomorphism maps a critical point. The generators of this space correspond to pairs critical point of index K plus the orientation. Okay. So
one thing slightly bothers me because okay, we use reduced homology.
Here we use the standard homology. Here is
here's standard, but didn't we write that? Okay, this is reduced.
Here is reduced. Okay.
Okay.
Here is,
so I wonder about index 0. And
okay, that's good that it's good that you're bothered. Do it yourself. It's the case is that it's everything is okay if the index is 0, because if the index is 0, this is empty. And you have a space. We have if index is 0, you don't pass through this. You just stick at here. So if index K is 0, then if K is 0, then this is a 0 space. So this is not a relative homology. This is like an absolute homology group, and this is an absolute homology group of a K of a discrete space with K points. Okay. If K is 0, then you don't need this step. You just look at this guy. This is 0, so this is like the absolute homology group of the K point space, which is ZK immediately. All right. So we have an identification of CK, and now we want to define understand the map. And the map is can we define a map? Let me try to define a map using homology, and then this is like the standard approach in algebraic topology, at least in topology of manifolds. Try to define a map, and if you can define it without choices, then it's a good map. Then it is a good one, and then you strive to maybe not prove, but to convince everybody that it's a good map. Sometimes it works, sometimes it leads to fantastic theorems that are eventually turned out to be wrong. So we start with hj of mk minus 1. What can we do? I omit for the moment z coefficients, okay? So that's for the moment. We can go for hj minus 1, mk minus 1, z, okay? That's the derivative in the long exact sequence of a pair. Is it okay? So we have the long exact sequence of the pair, which is hj of mk minus 1 goes to hj of, sorry, maybe I will just write you in an abstract way. What is the long exact sequence of a pair? hj of ab goes to hj minus 1 of b, goes to hj minus 1 of a, goes to hj minus 1 of ab, goes to hj minus 2 of b, and so on. And if you never saw the long exact sequence of the pair, so exact means the composition of two maps is 0, and the kernel of each map is the image of the previous one. So, for example, this is inclusion. So you have a cycle in B. You considered it as a cycle of A. So B is a subset of A. All right. So then you can. So this map is a relative cycle. So you have a cycle in A, and you consider it as a cycle in B with trivial boundary. So with no boundary on B. And then this map is the most interesting map. You have a cycle that is relative. So you have like a disk with a boundary on B. Think about it like in here. You have a disk and a boundary on B. And then you forget about this disk, you consider only the boundary. So this is the boundary map. You forget about this disk, you have the boundary of a disk is a sphere. So the boundary of a relative cycle is an absolute cycle in B. So this is this map here and here. Okay, so this is like how you construct the long exact sequence. And then you can map it to hj minus 1, mk minus 1, mk minus 2. And this one is also a map of the long exact sequence of a pair, but is a map of a different long exact sequence of a pair. Okay, so this is one exact sequence. This is another long exact sequence. This is for the pair mk minus 1, mk minus 2. That's why the composite of these maps is not 0. Okay. So we define the map, and then we will argue that this map is precisely the Morse chain complex. So before we pass to it, let's check that. So the composite here is the composite. We call it dk. Let me check that dk minus 1 composed with dk is 0, because that's what we want to have. If we don't have it, we are completely. So we have a map from hk of, and sorry, I should say that this is dk if j is equal to k, of course. So we have hk of mk minus, maybe the same color. There's no reason for changing colors. mk minus 1 goes to hk minus 1 mk minus 1 goes to hk minus 1 mk minus 1 mk minus 2. This is the first map, so now I change the color. So this is dk, and now I change the color, and then I go to hk minus 1 mk minus 2, and then I go to hk minus 1, sorry, hk minus 2, hk minus 2, mk minus 2, mk minus 3. So this is the second map. Let me just dk minus 1. But then you see that which part? mk minus 1, that this part is a composite of two maps in the same log exact sequence. Composite of two maps in the long exact sequence of the pair mk minus 1. No, sorry, mk minus 1, mk minus 2. So this composite is 0. So this composite is 0, so the composite of all maps is 0. All right. So now we want to argue that dk is equal to the count of trajectories. And this is the moment where Nicolaescu puts a little, just a little under the rug, and you will see how it works. On the next page, I will have a long homology groups, which are a bit a scary set of homology groups, which I wrote down. But you shouldn't be too scared too much. So recall that yk, we had mk, and this was yk. And the notation was that this is the lower boundary. So again, excision homomorphism, this is excision, tells you that the homology, the relative homology group of this guy modulo that guy is the same as the homology group of that guy modulo this guy, because you cut out everything that is below the level set k minus half. Okay, so this is like, this is maybe I just all right, so I uploaded the notes so that you can come back to the notation if you need. So we have excision homomorphism, that is excision isomorphism. Okay, so this is like replacing the big space with the small space. Why do we use the big space? Well, the big space will be used in the last and the most painful step, and painful from the point of view of algebraic topology, not from the point of view of the details of the argument. All right, so this is like the excision. And now you see we have a manifold with boundary, and we have an isomorphism of hk minus 1 to this part. So what is this isomorphism? You probably know that there is something that is called the Poincare duality. If you don't remember what the Poincare duality is, then Poincare duality tells you that if you have a closed manifold, let me just make a side remark, closed manifold, then Hn of x is isomorphic to H dim x minus j of x, and this is Poincare duality. From the, if you're not very familiar with that, this is there are several constructions of it. my favorite construction when I was a young young student was that it's the Hodge-star operator on differential forms. But there are different perspectives. Once we have established the Morse inequality, the Morse Smale Witten lemma, then Poincare duality will be precisely reversing the function f, replacing function f by minus f. Anyway, Poincare duality is a very deep operation, and you can go very far with that operation. Okay, so this is a Poincare duality, but you can have Poincare, the next stage of Poincare duality, if you have X is a manifold with boundary, then J of X is isomorphic H dim X minus J of X mod relative boundary. So this is the second step. This is referred to Poincare duality or Poincare-Lefschetz duality. And then if you have the boundary, the last stage, if you have AB and the boundary of X is A, disjoint sum with B, then you have the most general statement, dim X minus J of X B, which is like replacing homology by cohomology. All right. So here we are using this. The boundary of YK is a union of the lower boundary and the upper boundary. So we have the Poincare duality over here. Okay, and now the next step is the hardest to understand if you are not familiar with homology groups. So, and if you're familiar, it's the nicest. It's the evaluation map. So, what is the difference between homology? Sorry, one question. Am I too slow or too fast at this moment? I don't see you, so I don't see if I'm too slow or too fast with these details. So if you say that I'm too slow or too fast, then just you can either say, or you can click go slower or go faster on the voting on records. Okay, because you might get sorry.
So, as far as this, let's say tempo feedback and etc. So on topology 2, there was singular homology, and singular cohomology was not even defined.
Okay.
So I didn't speak up because I decided that I'll probably just look at the definition after the lecture, but it might not be.
So this is a moment where you have to use cohomology, and it's okay. Okay. There might be also some people that are logged in, but just playing Baldur's Gate 3, so maybe like 3 people in feedback is enough to proceed. So just one explanation for basically for everybody, because we have a chain complex CK dk with dk goes to from CK to CK minus 1. And then we can define like the dual space. We have a chain complex over Z, so CK is like a Z module, okay? So we have a map define CK star to be the homomorphism of CK to Z, like a dual space. And then we have a dual map, dk star, but dk star goes the other way. So if you have the passing to duality reverses the order. So it goes from CK minus 1 to CK star. So now you define kernel of dk star divided by, exactly the same tells you that dk minus 1 star is 0, dk star h star of is called HK with upper K, which means that it's cohomology. So normally you should write K. If you have cohomology, you usually write K on the top. If you have homology, you write K on the bottom. But if you have stars and K, it's more complicated. So that's why I used this notation. In particular, you can think of cohomology as something dual to homology, and expect. And for example, an example of cohomology groups are the RAM cohomologies with the derivative on differential forms increases the degree. So if you differentiate one form, you get two forms. So normally you would expect something like, let me just write it in some color, that HK is something like HKZ, okay? Expect. And this is almost true. So this is true if you work over a field. But in general, it's not true. Because in general, it's not true, for example, because the deepest explanation is that the home functor is not exact, is not left exact. All right, so normally you don't get an you don't get an isomorphism, but if your space is but if you work over if you work over a field, you get an isomorphism. If you work over Z, you get a map. You have a short exact sequence. And if I make a mistake, then correct me if I make a mistake. MZ to home of M Z to 0, and here is something that is 0 if HK minus 1 is 0. Okay, so unless I screw up the arrows, maybe I will just.
I suppose it's conversely.
You suppose
because,
yes,
because home is left exact when you fix left variable.
Okay, you know, the main problem is that saying whether something is, you have problems with distinguishing which side is right or left, or what is skirt or what is address, and I have problems saying whether home is left exact or right exact. So that's something that I always. All right, so you have 0 goes to home.
It's left because tensor product is right.
Yeah, but you know, it's like skirt and dress dilemma. MZ Z goes to H K of MZ. So for a manifold, and this is it's just for a topological space. It works for a topological space. Goes to, well, should I say a swear word or not? Maybe I will use a swear word. An object that you don't need to know what it is. It's x1 of H K minus 1 M Z 0. So this is a short exact sequence, but this guy depends only on HK minus 1. So just ignore this object. This object will be 0 in our setting. So we come back here. We have homology group, and we have and we know that what is this homology group? Well, or maybe what is this space? this is the space. I want to say that this is an isomorphism in here. So what is this? What is this space? No, sorry, what is this space? We have the top boundary, and we have yk. So we discussed that yk is that that this space, or my yk minus 1, it's okay, minus, it's a bit chaotic now. It's because I make a long digression, so maybe it was a too long digression, so that we lost, I lost the manifold from sight. So we have this, we are here. We are here, and we have this space is generated, as we said, by the classes of stable manifolds. So by the relative classes of the stable manifold of critical points. Okay, that is what we already discussed. So what is the homology of this space? This space is this manifold with the relative boundary over here. So how can we look at it? We can look at it by inverting the function f, and then this becomes the lower boundary. So this space, so the homology of this space, or I forgot the brackets in here. So the homology of this space is spanned by the unstable manifolds of the critical points. So in here, in here. So this is when we look at this picture from the opposite side. So this space is spanned by the critical point of index, is spanned by the stable manifolds generated by the unstable manifolds of index k minus 1 critical points. Okay, in particular, the homology groups of this space are concentrated in a single dimension. They are concentrated in dimension equal to m minus and k minus 1, which is the dimension of the sphere, the dimension of the unstable manifold. In particular, the homology groups one dimension below are 0, because they are concentrated in a single dimension, so in other dimensions they are 0. All right? So this tells you that the homology groups of this are that if they are, the one lower is 0, so this guy, this short exact sequence, which I can refer to, because you might want to check it later, what is this exactly? This is called universal coefficient theorem, which you can look up on Wikipedia, but you can also look it up in Hatcher, and you can look it up in Spanier. When I was one other digression, when I was young, I hated Spanier, but then I know how to read it. If you want to, Spanier is not a book that you should read from the beginning to the end, but it's a book for where you want to look at. If you want to find the result, if it's not in Spanier, it's probably not true. Spanier will soon be subsumed by the book by Stefan Friedl once he finishes it with 2,000 pages of rigorous algebraic topology. Okay, so this is an isomorphism, because this guy, if the homology group below this, if hk minus 1 is 0, then this is 0. So this is an isomorphism because it's a short exact sequence. If one term is 0, this is 0. So this is an isomorphism. So what we have a composite of maps. And actually, the composite of these two maps is the most interesting for us, because this is a map that oh no, what I wanted to say, we are okay, so this is a sequence of isomorphism. Let me just rewrite it. We have a sequence of isomorphism hk minus 1 of mk minus 1 mk minus 2 goes to hk minus 1 of yk minus 1 minus yk minus 1 is equal to h upper k minus 1 of yk minus 1, sorry, m minus k minus 1 of yk minus 1, the top boundary of k minus 1, and this is equal to the hom of h m minus k minus 1 of yk minus 1 d plus of yk minus 1. All right, so this is a sequence of isomorphisms. And recall that we had a map hk of mk minus 1, and that was our differential going to hk minus 1 of mk minus 1 mk minus 2, and this is the same as hk minus yk minus 1. No, sorry, yk d minus of yk, but this is the same as hk of yk d plus of yk minus 1, because these two overlap.
I'd like to ask a question about what you claimed a while ago, that this homology group inside hom is generated by unstable manifolds. Because it's by the construction, the homology group is generated by a singular simplices, and basically singular homology knows nothing about manifold structure on.
All right, so if I say that hk of, let's say hk of yk dyk, then we proved that this is the same as hk of dk cross dm minus k as k minus 1 cross dm minus k. That's what we discussed, yes?
Yeah.
So that's hk reduced of the wedge of fsk's, okay? And if I say that the homology group, if I say that the homology group of this guy is generated by the classes by the stable manifolds, then I use this isomorphism, okay? So this is the homology group, and these are the generators. The generators are in, I can choose a generators of the homology group to be the classes corresponding to stable manifolds.
Because they were glued along stable.
Yeah, they are glued. These are these guys. This guy is the stable manifold, and this is like the foot of the stable manifold. So that's why I'm saying that the classes are generated by stable manifolds. That's what I mean. This is like this is the precise meaning. And of course, the same game you can play with unstable manifolds to tell you that h, and now the dimension of the unstable manifold is m minus k of yk d plus yk is the same as c, is the same as ck.
Thank you.
All right, so this is the same that the homology group, the relative homology group with top boundary is generated by this class. All right, so let me just come back to this guy. We have a map from, we have now a map from, so this is like our composite. Let me call this iota, hom, and this is an isomorphism, hom of h m minus k minus 1 yk minus 1 d plus of yk minus 1. And we have and decay under this isomorphism is essentially, this is like the same decay, okay? Because this is a sequence of isomorphisms, and this is an isomorphism, that is the composite. And now Nicolaescu says this. Let me copy this map and maybe even to the third page. We have hk of yk d plus of yk minus 1 dk, too long, arrow too long, dk of hom h m minus k minus 1 y k minus 1 d plus of yk minus 1 z. All right, and let me draw the picture, and now there will be a thing that is put under the rug. If you want to have to fix it, it's a good exercise. I won't fix this, but I put clearly what is hidden under the rug. So I have this homology group is generated by these classes. I have this homology group generated by these classes. And Livio says this map claim without proof. This map takes a class A in yk hk of yk d plus of yk minus 1 and a class B in hm minus k plus 1 of yk minus 1 d plus yk minus 1 to the intersection index of dB as submanifolds of d plus of yk minus 1. Okay, so this is like, what is the map? How do you define the map to homomorphism spaces? A map from this to the space of homomorphisms is exactly, you take an element in here, take an element in here, and you produce a number. That's like carrying in many programming languages. If you have a map from this to homomorphism, so to the dual space, it's like give a pairing from this times this to z. So that's the number. And this map takes A and B to the intersection index as submanifolds of that guy. And I don't prove this claim because Livio didn't prove it. Not proving. How can you try to prove? Well, you have to go more deeper in the definition of the intersection index. So for example, you compose this map with, you show that this map can be composed with a map to, can be factored through hk d plus yk minus 1. So factor it through this, factor it through hm minus k minus 1 to this, which you can do. So if you factor this to this map, then you can show that this is a map that somehow factors through d plus of yk minus 1 to hom hm minus k minus 1 d plus sorry, m minus k d plus of yk minus 1. If you can show that this map factors through these spaces, for example, and how you can show that it factors, well, if this is a part of the long exact sequence, so you need to show that it's mapped to 0 when you compose it with the next stage of the long exact sequence, and the same in here. If you show that it maps, then you have to argue that this map is Poincare duality, and then you get the intersection index. So that this map is Poincare duality. Usually, the statement is that whatever you do using Poincare duality and inclusions and boundaries is canonical and it's Poincare duality, but we don't prove it. So I leave the proof. It's not. It's like playing with homological algebra. I can give you another proof of an analogous result as a master thesis problem. Master thesis problem, which means fixed signs. But anyway, what is this intersection index? We have a class in here, which is the stable manifold. We have a class in here, which is the unstable manifold. So the intersection index of dA and dB is precisely the signed count of trajectories. Okay, so if we prove that this map is the intersection index, which we don't prove, then this immediately tells us that the map that under the isomorphism hk of mk fk minus 1 to ck to our chain complex k minus 2 ck, the map dk and the map that we defined, that they are the same maps. This gives us immediately the same statement because this is the signed count of trajectories. Okay, so once we unravel this all definition, so this guy goes to this, that this is the intersection index, then we discuss that this is the map, and lo and behold, sorry, one problem. You don't show this k minus 1. So in particular, dk plus 1 is 0. All right. So this is like showing that the Morse chain complex, where are we? This is the map that is defined like homologically, without any reference to vector fields. This map is defined using the gradient like vector field. This map is just the composite, remember, hk minus 1 mk minus 1 to that. So this is like a composition of this map, the boundary map here, and the inclusion-induced map here. All right, so far so good. And now we have the chain complex of maps, and we want to show that the homology of this chain complex is the homology of the manifold. And now this is the technically maybe easy part, but conceptually, It requires more knowledge. So are you familiar with Meyer-Vietoris sequence?
Yes.
Okay. And do you know how to write Meyer-Vietoris sequence for more than 2 spaces? Like you cover your space with like n-fold spaces, n open sets instead of 2 open sets, like 5. What you can get? How can you proceed with the Meyer-Vietoris sequence? It's not taught, I guess, during.
It's not. So at least I can't. I have no idea immediately.
Yeah, what is an idea immediately?
I have no idea
No idea. Okay.
immediately.
Okay, because it's not taught because it's more complicated. It requires a new tool which is called a spectral sequence. Is anybody familiar with spectral sequences?
On some really basic level, maybe.
Yeah, that's a basic level.
I know. I don't know. I don't know what a spectral sequence is. I only know that it exists.
Okay. So what is a spectral sequence? So this is referred to Leray-Serre spectral sequence. Nicolaescu doesn't prove it, but but he refers to some proof in Hatcher book in theorem 235 Hatcher, assuming that this is the yes, assuming that is Hatcher book. So we have the chain complex Ck of M of C, maybe Cj of M of a manifold M. Well, actually, it may be a topological space, or a CW complex. Okay, we have the singular homology, and we have we have presented M as a union of MKs, and M1 was a subset of M2, and so on. So you see, for quite a while we were working with MKs, even though we immediately, in the previous stage, we immediately passed to relative homology by excision, Y, boundary of Y, or decay, boundary of decay. But at the beginning, we were playing with MK for apparently no reason. But now we have now we see the reason, because we exhaust M with increasing family of subsets. Okay, that's like if you think about M as if you try to think about M in a different setting, like a CW complex, then you exhaust the CW complex by adding cells of higher and higher degree. This is a very good intuition for the statement. So M is exhausted by MK. So now you have this inside CJM, which is a vector space or a module over Z. You can find, and this like M ends up with MM, which is M. CJ.
So we assume that there are only finitely many MKs.
Well, yes, because this is finite dimensional. All right.
Yeah.
You can work with infinite dimension, but it's MM, and it's a subspace M some K 0. All right. So this is like you have a map, and we have a descending sequence of subspaces of your chain complex of Cj of M. Okay, this is, and now you can work with cellular homology. You can work with CW complex homology. You can work with any homology, basically any homology theory you want. This is like a basic explanation, and you have the derivative d going to Cjm. Okay, and this derivative goes to, well, it preserves the filtration. All right. So what you can do, what would you like to do? You would like to do the following operation. We have the derivative dj, and I will write it djm minus 1, djk, and so on. All right, so we would like to say, okay, look at Cjmk over Cjmk minus 1, and then this chain complex to Cj minus 1 of mk minus 1 divided by j minus 1 mk minus 2. Okay, so this is the map induced by passing to quotient. You mod out, instead of this, you take the quotient. And your map, you have an induced map that goes from the quotient to the quotient. So call it d capital D jk0, and this map squares to 0. This is aj of mk minus 1. This is hj minus 1 of mk. Sorry. This map squares to 0, and the homology of this complex let me just copy it here. The homology of this complex computes, well, the relative homology group. This is like the space of relative chains. Chains modulo will be chains modulo the boundary, so computes homology of sorry, I'm saying something wrong here. There's a mistake here. And here is mk, of course. The grading is not changed yet. mk minus 1. All right. But you have the maps, but you can have a map from this space to, or from the, so suppose you have an element in here that goes to 0. In here that is mapped to 0. Then I can find an element. Which way did it go? If I have an element in here that is goes to 0 in here, then I can find an element that it forgot it. Sorry, I want to wave hands, but then you have if I have a map from this guy to that guy, from this quotient, so I look at the I look at this. Now, suppose I have an element that goes to 0, under this map. Then maybe it is hit. Maybe it goes to 0, not just because it's 0 under dj, but it's 0, because it lands in this space. Okay, if I have an element in here that goes to whose quotient is non-zero, but goes to 0 under this quotient map, then I can construct the map from then maybe it's sorry, if I have an element in here that goes to 0 under this map, then maybe it comes from an element in here that is mapped to this space, not just to 0 under this map. And if I look carefully, I can construct the map that is h that goes from the homology of this complex, so hj of mk minus 1, to the homology to hj minus 1, mk minus 1, mk minus 2. So by what is called diagram tracing. If you never saw this, try to define the map by saying, by what I told you, that if I have an element in here that is mapped to 0, then I can look at the image of this guy under, then if it's mapped to 0, then it has to sit here. And then I can by diagram tracing, I can show that there is a well-defined element, well-defined map from this guy to that guy. So from homology of this complex to homology of that part. And then I repeat the construction. Which is a bit painful. In general, if I have an element here that is mapped to, whose representative is mapped to 0 under this map, then maybe it comes from an element here that is mapped to 2 levels down. Actually, it's mapped 2 levels down in this direction. And then I can iterate this procedure. I iterated, and what I get in the following is what is called the spectral sequence EPQJ with DJ going from EJ PQ to EJ P minus JQ. I never remember these indices, and I always have to check it. And the key point is that E1 PQ is H P of mk minus 1, and D1 H1 PQ HP mk minus 1, Q minus 1. So I gave you the motivation. Now I give precise result which we will rely on. MQ minus 1, MQ minus 2, which is our differential. And the key point with the spectral sequence is that the kernel of DJ PQ mod the image of the kernel of DJ, and the image divided by the image of EJ is EJ plus 1, with the indices that you have to remember, that you have to check always. And so this is the differential, and the other phase is that the total homology, So you iterate this procedure, you iterate once it stops, but you don't want to say where it stops but it stops because everything is finite, every chain is bounded, but the total homology, the total sum of the spaces that you get is our original homology group. Okay, so this is like a spectral sequence where you can read it in Hatcher, or there is a user's guide to spectral sequences. But anyway, the key point is that you start with a chain complex with something that is called a filtration, like exhausting it with spaces. And you have a differential that preserves the filtration so that this image goes to that. Your first stage is look at this guy and the map between these guys. The kernel is homology of this part. But then you can go down and the first stage, so this is like the zero stage. But then you can define this map by popping from here to here. And then you get the map from hj of kk minus 1 to hj minus 1 to k minus 2. And then you iterate this, and then you have a map which is precisely, when you look closely, it's precisely the map, precisely our differential, precisely the differential that we defined. It's like diagram chasing. We can do this, a part of this diagram chasing during the classes if you want, which will start later because we go over time, but I don't want to stop before I stop. So we have and we iterate the procedure. And the procedure, normally, the procedure gives you maps that go from here, and they somehow encompass the part of differential, the part of the cycles that are mapped to different filtration, because you can have a map, a cycle here that goes somewhere in here. So this gives you, if you look at diagram chasing, this gives you a map from here. If you want, it's it's much better to watch a video with diagram chasing, with someone doing diagram chasing, than trying to decipher all the kernels and co-kernels in the spectral sequence. But the upshot is that the total homology, each time you define this space, that you iterate the procedure, and the total space is the homology group. In our setting, the situation is much simpler. Because this differential, because we have this space is 0 in precisely 1. So without giving all the details, I can't prove it, but it's actually easy. In our situation, D2 is D3 is 0, because Hj of mk minus 1 z is 0 everywhere except for j equal k. And this is the key point. That's why I told you that we will use it. So this is j is equal k. And then h star of m is equal to E2 PQ, which is just the homology of the complex H k mk minus 1 goes to mk minus 1, mk minus 1, mk minus 2, hk minus 2, mk minus 2, mk minus 3, and so on. All right, so this is like the last stage, that the homology of this complex is precisely the homology, the singular homology of the manifold, uses Lara's spectral sequence, which collapses, which is equal to the second page. And so the round summing up sentence is that because this homology is 0 everywhere except for j equal k, then the long exact sequence, then the spectral sequence collapses, and you get right homology. And if you prefer, you can try to do it inductively using Mayer-Vietoris. And maybe it's instructive to do it, but this is like an occasion to see that there are some objects like spectral sequences, and they are worth, maybe sometimes they were worth using. So that's all for the lectures. I stop recording. We resume at 10:20 the classes.